Okay, it's a great pleasure to introduce Professor Saibal Mukhopadhyay. He's visiting us from Georgia Tech. He's a Joseph M. Pettit professor in the School of Electrical and Computer Engineering at Georgia Tech. And Saibal got his PhD degree from Purdue. Around the same time I got my PhD degree, actually. I think so, same year, yeah, 2006, right? Yeah, 2006. And then he went and did a stint at IBM T.J. Watson Research Center as a research staff member, where he did internships previously, and then moved to Georgia Tech, and he's been there ever since then. Yeah, he's enjoying it. And he is directing I'm going to read the center, Cognisense, a center on cognitive multispectral sensor based on the JUMP 2.0 program, supported by Semiconductor Research Corporation and Defense Advanced Research Project Agency. And his research interests include a lot of things, including secure, intelligent, energy-efficient integrated circuits and design of smart sensors. He's an IEEE fellow. He has a bunch of awards, which I will not go over, but I'll leave the floor to him. He's going to talk about an exciting topic today, which is dear to my heart also, which is computing in memory, analog. But he's going to talk about some interesting applications beyond DNNs, I believe. And I'll leave the floor to you, Saibal. Welcome. Thank you. Please welcome Saibal.
Thanks, Onur, for the introduction and currently hosting me. This is a pleasure. This is my first visit to ETH, and the weather yesterday was amazing, so I couldn't ask for better. Okay, so I'm going to talk a little bit about some of the work that we have been doing in this space of computing in memory. To be more precise, analog computing in memory. Again, do I go forward here or this one? You just have to click this. Huh? Oh, this one? Oh, okay. Okay, so computing in memory, I'm sure this is a very common concept today, right? We know in a traditional von Neumann architecture, we tend to have control and the logic sitting at one place, and the data is stored in the other place, and that creates the additional energy that we need and the time that we need to move the data between the compute and the memory. So we can address that concern by going into this notion of compute in memory architecture, where the idea is really that the compute gets more closely integrated within the conventional memory system, and that memory could be SRAM, DRAM, NVM, different styles, and depending on what kind of applications we're going after. And a lot of research have shown us that there's a benefit in doing it. It allows us to reduce the data movement, give us better energy efficiency and potentially higher throughput. There's tons of work on that, and some of the work came out of Onur's group is one of the pioneering work along this domain. Now, if you take a step back at a very high level, think about what do we mean by computing or processing in memory. There are different ways people think about it. At the one extreme, where really what you have is this memory blocks, right? And then you connect them through some sort of a network, bring in the processing and the computing engine as close to the memory as possible. There, often we call it processing in DRAM, processing within a near memory, so on and so forth. Then you can come a little bit closer, some more finer grain integration, where what you say, let's keep the memory like the digital memory, right? But bring your logic as close to the peripheral circuits as possible, so that as soon as you access the data, you can do some digital computation on the data and write it back if you need to. Or you can go all the way down, where you say that every bit cell within the memory does a little bit of compute. That's the finest possible grain of integration that you can think of how do you bring in compute and memory together. So you put a little bit of compute within every bit cell, you put a little bit of compute every word line, every bit line, or every row and column. So you have a compute integrated within a memory block. In general, as you go from right to left, you get an improvement in energy efficiency, at least theoretically, because you get more concurrency in computation, you get more parallelism, less data movement. But and as you go from left to right, the design complexity shifts more from the circuits to microarchitecture to the system architecture, right? So if you are on the leftmost side where you are trying to integrate compute very closely, very fine-grained within the bit cell, within the peripherals, it becomes a circuit design challenge. And it potentially can give you a lot of concurrence in the data movement. But on the other hand, as you move towards the other side, the challenge becomes more on the microarchitecture and the system design, but also much easier in some sense because less disruptive to the overall circuit fabrics of the memory system. Now, the reason these concepts, the ideas of computing in memory is not new. I think it goes all the way back to 1960s and the 70s when people started talking about bringing logic within the memory system. The reason we are talking about it a lot these days is artificial intelligence, deep neural network, which can benefit greatly with these classes of computation. Now, DNNs are used in two places. One is more on the server side. We're not going to talk about that. We're going to talk about computing more towards the sensor, that is in the edge systems where you're getting real-time data, processing it, and generating intelligence. There is several work which have showed that, your perception engines, right, which takes data from the sensor and try to make sense out of it, and the kind of DNN that we use there, we can replace those DNNs or we can realize those DNNs, not replace them, using different classes of computing in memory structure. Again, we're not going to talk about this. This is a very well-established field. What I'm going to talk about is, are there applications of computing in memory that goes beyond accelerating DNN? And what else can we do with analog computing in memory structures? So with that, let me come to the two topics that we will try to talk about today. One is a notion that where we are going to talk about using analog computing in memory right at the sensor, even before you digitize your data. So can I operate directly on the analog data to do what? Essentially to address a major challenge in sensing, edge computing, or for that matter, in computing in general. That's what we call analog data deluge. So we're going to talk about that. The second part of the talk, we will talk about a different applications where we often need to take complex decisions at the edge, which requires us solving hard optimization problems like SAT, like least square, like graph problems. We're going to talk about there are some very interesting ways that computing in memory can help us in making this real-time optimization problems done faster, potentially at a lower energy, at a lower cost. So I'm going to talk about some examples from this, and hopefully that will give us some more insights and potential ideas of expanding this field in the future. So with that, let's get started with the first part. So what is analog data deluge, right? This is a very well-known curve, well-known figure or graph that has different versions of that has been floating around for a time, which shows in the x-axis is the years, and the y-axis, the amount of data getting generated through the sensors that we have in the world today. And the projection is that even as we speak now, the amount of data that we generate is way more than what we as a humanity can consume at a given point of time. So we are generating way much more data than what we can even consume. So the question is, why we are doing that? That's one part of the problem. The second part of the problem, that how do you make sense out of this data, which is way more than what humanity can consume? So how do you, and this problem is known as analog data deluge, that we are just deluging ourselves with way too much data. The question is, are there examples of how do you, is it the bell for when the new class, the next class? Okay. Now there are examples of this notion where we sense a lot more than we process. And one of the great example of that is actually human brain. So it turns out, depending on whom do you talk to, that the rate at which our eye captures information is in the order of tens of megabits per second. but the rate at which our brain can process information is in the order of hundreds of kilobits per second. So biology has a way to deal with generating very high dimensional or capturing very high dimensional signal, but make sense out of that with an extremely low data rate processing. So what we wanted to understand is that, can we replicate to some extent these biological concepts into an engineering system? And that leads to the first part of how we are going to use computing in memory. So let's take before we go there, let's take a step back and think about how we do that in today's sensor, right? If you have a camera today, if you have a drone which is using a camera to sense the surroundings and taking a decisions, or radar, whatever it is doing, at a very fundamental level, whatever is your sensing modality, what you do is the following. You have a sensor front end, which might be a radar, LiDAR, imager. You sense the world, and as soon as you sense the world, you digitize it right away. And then you send the digital data to potentially a different chip, which does what we call our onboard processing. And you can apply DSP, ML, whatever we need to be able to do perception, right? So the key part is that we get the analog signal, we digitize, and then we send the digital data for my backend algorithms. What's the challenge? How do you improve quality of a sensor? We use more and more pixel, and we sense them we run them at a higher and higher speed, right? More frame rate, more bandwidth, more pixel resolution. But as soon as you digitize everything, you lead to large amount of digital data that's getting generated. That's one part of the problem. But the second part of the problem is that when you are doing this, you are running your analog to digital converters continuously, which are power hungry, particularly if you're looking at high data rate systems, sensors like radars. And you're also transmitting a lot of data. So there is a good amount of power being consumed in doing the digitization and the data transfer. And also, all of this data is eventually being thrown to this ML pipeline at the back, right? If you take any ML algorithm, it doesn't matter how small or how large it is. If it has to process more data, it is going to do more work. There is nothing we can do about it, right? So this digitize everything, every pixel creates more data, right? It also creates a lot more power because ADCs, a lot more ADCs running at a faster rate, and a lot more data transfer through the IOs, and finally a lot more power distribution in the compute. So the question that we started looking at, and particularly in the center that Onur just mentioned, is how do we solve this? So how do you solve this? Mathematically, what you need to do is reduce the dimension, right? So you are generating, getting analog signals at a very high dimension. By high dimension, what we mean? Large number of pixels, that is the spatial dimension, and they're sampling pretty fast, that's the temporal dimension. So what we get is a very wide dimensional, high dimensional signal. But at the end of the day, if you think about it, the decision I'm going to take is a very low dimension decision, right? If I am a drone, right, I'm trying to decide, I'll basically go up, go down, go left, go right, and some combination of these angles. So I'm using a very high dimensional data to generate a low dimensional decision. The question is it possible for us to reduce the dimension right at the sensor to generate information in a different space where it is a lot more concentrated, and then design the backend algorithm to take decisions out of that concentrated space? You can do that, and one interesting way of doing it is, particularly the spatial part of the data reduction, is through computing in memory. Now, how do you do that? We're going to come to that, but let's see what happens if I can do it. So let's assume that, we start with a system which has m pixels. We're going to let's use radar as a potential sensor here. The reason is radars are wideband, that requires ADCs running at a very high speed, so they do consume a good amount of power in digitizing the data. So if you have an AM antenna arrays streaming data, right? Instead of digitizing everything, if I can do something to reduce the dimension from M to N, where N is much smaller, so let's say 1024 dimension coming in, 16 dimension going out. So I reduced the number of ADCs by a factor of 1024 to 16. That directly gives me less power because I need less ADC, less data, and less compute for the backend algorithms. The challenge is we have to do it in a principled way so that I preserve as much information as possible. So one way to do that is essentially, again, if you're familiar with specific type of, AI model called state space machines, this is we do there. Basically, what you do is that you bring in the inputs and then you make it a linear transformation on that input, transfer it to a lot more denser space, right? We do that. This is a very classic technique in linear algebra. And if we could do it, then if I bring in my analog input, I pass it through this linear layer, which has a less number of input than the input. How do you create that linear layer? There are mathematical signal processing theories to do that. I'm not going to go into the mathematical aspects of that. But at the end of the day, you generate a lower dimensional signal. The math of this is not new. We know how to do that. There are classic algorithms of deciding how do you generate these weight matrices. There are algorithms which tells you that how do you adapt this weight matrices over time. The challenge has always been that this all looks good, but in practice, how do you accomplish this goal that where input is analog and the output is digital? And I know how to do that for one signal that's called ADC. I may be able to do that if I have a few more signals that called composite ADCs or computing ADCs. But now if I have a really large number of input, like 1024 channels, and I want to mix all of them through an algorithm, generate digital data, we do not know how to do that efficiently, or at least we did not know how to do that efficiently till a few years back. This is really where the computing in memory comes into picture. Now, one thing we have to be careful here that how do you, what we are trying to do here, right? We're bringing in an input vector, multiplying that with a dense matrix, generating an output vector. So internally, what I'm doing is a vector matrix multiplication. The challenge is these weights, ideally, they should be analog values. I can do that with a resistive RAM structures and whatever. The challenge is not reliable. Changing that weights are going to be a nightmare, right? It takes a lot more energy to write an RRAM. So we don't want to go there because we do want to change these weights adaptively as the drone is moving through its environment, not every nanosecond, but maybe every millisecond. So a good way to do that would be through an SRAM-like structures, which it is easy to write. But if I do an SRAM, then the problem becomes, how do we realize the weights, right? I cannot do a single bit weights, so I need a multiple bit weights. So how do you recognize, deal with this multi-bit weights? These are the standard problem that people have been looking at in the analog computing in memory in the context of DNN acceleration. But now these things remains important. But on top of that, we get another challenge that the inputs that are coming in are analog itself. So one of the structure that we have been looking at in our group is based on this 8T SRAM structure. The concept is reasonably well known and simple. Basically, you have your SRAM cell. I don't think this is, okay, let me use this. You have your SRAM cell that is storing the data, and then you bring in one of the node connected to a 2T read path. This is what we call 8T SRAM. And this 2T read path, you have two transistors here. One of them is going to be on and off depending on what is stored here. And second one is connected to your word line. This is where you apply your input. If the input is 1 and 0, this entire path is going to behave like a digital path. And this is most of what we mean by analog computing in memory in the CIM world, that we have either 1 or 0 at this input. If it is 1, and if this is also what I stored 1, then I will have a finite amount of current. If this is 0, then if either of them is 0, I will have no current, right? So that's the dot product between two bits. But now if you go a step beyond and you think about that, what we have here is not a switch, it's a transistor. So what does a transistor do? It has a property called transconductance amplification, right? So if I apply a small voltage, if I apply a VGS at the gate of a transistor, the current through the transistor is GM VGS. So that means current through a transistor, depending on if you can bias it properly, has a linear dependence on the input voltage. If I make use of that fact, now I can transfer this not to a bitwise dot product or bitwise product, but a product between a bit and an analog value. So this current now will become basically an AND function between what is stored and the GMV in. So this is not your logical AND, it's a logical AND coupled with analog multiplication. And once we do that, then all of the cells which are connected to a bit line, for each of them, I'm going to generate a certain amount of current. It could be 0 or it could be proportional to the input voltage. And as I add them up, that gives me a dot product between a single bit vector and an analog input, an analog input vector. So far, so good, right? Normally, if we look at analog computing in memory world, what we do is that's primarily majority of the literature. We will look into this and then we will directly digitize whatever voltage that I generate out of this column. The challenge with doing that is that now, if I have an 8-bit word, I have an 8 different ADC. So eventually the number of digitization engine that I put in becomes too high, and all of the design gets dominated by DSC, or in this case, ADC power. That's not desirable, because realize at the end of the day, I want the dot product between this word, not each bit, right? And the input vector. Now, what do we do after we digitize each of them? We say that after we digitize, I get if I look into each of the column, after I digitize it, then I have to shift the digital word through a shift and add process, because I know that, if this is my LSB, whatever is the value here, and if this is the LSB, the same value here in the LSB should be 8 times larger than what is I have on the LSB side, right? So that's what we call digital shift and add. But we don't need to do that. The reason is there's an excellent process of shifting and adding in the analog domain that we call current mirrors. In a current mirror, what you can do, depending on how you size up the do mirror part of the circuit, you can actually, this may not be very clear, but essentially what you can do is that if you take an input current in, by changing the size of the mirroring transistor, it is possible for you to have an analog shift and add instead of doing a digital shift and add. Great, we can do that. And if I do it, then the advantage is I can reduce the number of ADCs, and this is what we call a binary current accumulation. All good so far. Now, normally what we do is that we look into the current. We do not work with the current. After I generate the current at the bit line, we essentially transform it to a voltage, and then we digitize the voltage. Now, that's the traditional way of doing the computing in memory architecture. But we started thinking of is that why? Because as soon as you are trying to convert current to voltage, either you are going through a capacitive option or through resistive option, both of them dissipates power. We don't really need to do that, because I can design an analog to digital converter right at the current domain. There is a field called current domain ADC. It's not our invention. Current domain ADC exists in the literature. People used to look into this quite often. We eventually moved more into the voltage domain ADCs because it is normally easier for us to think in terms of voltage. But here, since that voltage does not matter to me, what matters is the digitized output, I can actually remain in the current domain as much as possible. And then eventually, I'm not going to go into the circuit detail, but eventually I can get this accumulated current and digitize the current directly using a specialized structure that called a current domain ADC. Now, why are we doing all of this, right? Why do I go through this instead of voltage? I reduce the number of ADCs, I go through this for two reasons. Number one, as a memory designer, if you tell me that I have a computing in memory where 80% of my area is on ADC and the DSC, my reaction would be that's not a memory, that's something else, right? So one of the challenges that we started thinking of is that how do we make sure that a computing in memory looks more like a memory, not like a compute? To do that, you have to start thinking of how do you reduce the number of ADCs and how do you make them simpler and tighter. In the memory world, as a memory designer, we often talk about things called pitch matching. That if I have a word line and the bit line, every circuits need to fit within that. If you take a standard voltage mode ADCs, either it flash or SAR, any of them are very difficult to fit. So we ended up designing a layout where I have a little bit of memory here and a huge amount of compute in the ADC and the peripheral circuits down there. So we were able to solve that problem by going through these two approaches of binary accumulation and current domain. So now if you look at, this is the layout of our first generation of the chip in 28 nanometer, you can start looking at and seeing that this is my memory, and this is, I believe, was 128 cross 64, that is 128 cross 256 array. And you can start looking at all of our ADC peripherals is much smaller compared to what we have on the internal memory structure. So this gets us closer to the notion that I should be able to fit all of my peripheral very closely in a tightly regular integrated way within my memory system. I'm not going to go into a lot of the this overall architecture. So what it does is that at a very high level, this is your memory cell. This is the columns. This is exactly what we talked about, the BCA and the ADCs. Since your analog value is coming in, your analog signal itself is a fluctuating signal, so you have to do a sample and hold at the front end. So you need an additional circuit to doing the sample and hold so that you sample the analog input at the rate that you want, hold it, do the computation, come back. So it's almost behave like a pipeline system that we in the digital world are very familiar with. The only difference is that your front end of the pipeline is analog, the back end of the pipeline is digital. So the same clock you sample, the same clock is also used to sample the digital at the output. As I mentioned, you need to be able to write to this at a reasonable speed. So you need the standard digital peripherals. They cannot be very, very slow. They can be slow, but not extremely slow like what you would do in an NVM. Because, I'm not sure whether I have the slides there, but you do need to update them at the end of the day. These are first generation test chips. Again, there are more higher and higher generations. We have a couple of others after this. But the point is, the few things I would like to note here is that if you look into this particular figure, that starts telling us is that we wanted our area to be dominated by the memory, not by peripheral, because otherwise I don't have a computing in memory. I have some little bit of memory in a compute, right? So we were able to accomplish that goal to a certain extent. Ideally, if you look into a standard memory, this number tends to be around 80%, that your memory should be 80% of the total physical area that the memory block occupies, because the rest 20 is on the peripherals. We would like to get to that around 80 to 85%. So far in this design, we were around 60%. So it's not there yet, but it's definitely much better than many of the prior work. And the second part was critical is this number. Why is this number important? If you're using a computing in memory for a compute purpose like a DNN pipeline, the notion of a throughput and the latency are sort of in your control, right? You can hide latency. You may decide to run things slowly, but go a lot more parallel, right? So that you can get a higher throughput. You do not have that leverages when you're dealing with the sensor data. Because if your radar requires a bandwidth of a gigahertz, you have to do this thing at a gigahertz. If you do it at a 900 megahertz, you lost the point, right? If you do it at the 1.1 gigahertz, it's a little bit better. You do a little bit oversampling, there certain algorithm goes up. So one of our goal was, and actually our design target is to push this to up to 2 gigahertz The first version, we can get up to 600 megahertz. The second generation, we can get closer to 800 megahertz or so. We're trying to get to 2 gigahertz eventually. Looks like with 28, we can maybe able to hit around the gigahertz mark, but after that, we may have to go to 16. But the point is, a lot of these design techniques I was talking about, remaining in the current domain, do not digitize, don't go to voltage unless you have to. All of them helps in achieving this number. If you compare this with some of the other computing in memory solutions, you will see this number tends to be in the order of 100 megahertz or even lower. You get very high efficiency, but running at a lower frequency. In this case, the problem changes. You have to get to high efficiency at high throughput target. Not only throughput, high efficiency target, or rather high frequency target. So the efficiency was around 30 to 40 tops per watt. It's again, it's good. It's probably, this number should be, eventually we want to hit around 100 to 300 tops per watt. So still pretty far away from where we need to be, but this was closer. Now I'm going to come back to this plot a little bit later. So what this plot talks about is that how well the linearity of this entire computation is. So I'm going to come back to this later because this has a strong significance. Any questions so far? Yes, please. Please feel free to interrupt me at any point of time, ask question.
So this might be a very, yeah, okay. So, we are talking about computing in the sensor itself, right? So it might be a very novice question. So what amount of the entire power of the entire pipeline, so not just the sensor data, but the post-processing is actually done by the sensor conversion itself? Because if we are not converting, we're essentially reducing that power, right? So, but if the power of the entire pipeline is dominated by the later part of the pipeline, not the sensory, then
yeah, it's a great question. You will get a little answer to that to some extent as we start talking about the application space. We will have some results along that line. The answer is quite a bit, depending on which sensor are you talking about, right? Normally, if you are looking at kilohertz sensors like biological signals, that's a very different ballgame. But realize if the sensor, the power dissipation on the back end is proportional to the power dissipation in the sensor. Because it's not necessarily a linear mathematical proportional, but they're highly correlated. Because if your sensor is not generating enough data, then you should not be processing that much data. So power dissipation of the processor will go down automatically, right? Particularly, this becomes more, this correlation is stronger if your backend is also ASIC. Because if you are pushing it into a CPU or a GPU, the reason that this GPU is taking a lot more power, right? If you, let's say, take a sensor, push the data into a Jetson, it's not that all of the power that Jetson is taking is going into processing the sensor data. It has to do a lot of other stuff, right? So it's very unfair in some way to say that I have an analog, I have a digital accelerator, takes less power than the GPU. I mean, of course it's supposed to, because it doesn't do as much work. So the point is, if you look at the actual compute power that's being utilized to process the sensor data, depends on the power at the sensor, because power at the sensor tells you at how much resolution the data has. It is how much data sample that you're generating at every time step, and then how fast you are sampling. There is an entire interesting field called event-based sensing, which addresses this concern a little differently. So they basically, what they tend to do is that they will say that I'm not going to treat data as vector. I'm only going to see whenever there's a change happens in the sensor value, I'm going to create an event out of it. It works pretty well with the pixels and the cameras. We're not going to go into the details there. That's more than happy to talk about it offline. But if you think about all of the sensors which are looking at the input as a vector, like radar, like imager, there is a strong correlation between what you are doing. So long story short, take any DNN, say that my input is input image, take ResNet 18. run it for CIFAR-10 versus ImageNet. The same model, which one will consume more power? What do you guess? What's your guess? Same model, I'm running it for an ImageNet data versus CIFAR-10 data. Same model, which one will consume more power? Why? My model is same, because my input is more, right? So as the input goes up, it doesn't matter what algorithm you're using, it's going to take more power. So if I can take an ImageNet picture and think about, without losing information, I can transform the data to a CIFAR-10 size. I'm not going to call it an image anymore, and have your DNN work on that. It is going to have a less power, provided the conversion from this to this, from the high resolution to the low resolution or denser, does not overshadow. Does that answer? Okay. There's another question. Yes, please.
So in the context of drones and many other such applications, you may need great accuracy, because if you do something wrong, you have potentially costly consequences. Using an analog computation may, you may run into issues because of process variation. So do you propose, or do you have ways of how you can combat these issues?
We will talk about that in the next part. Do I know how to solve these issues? The answer is no. Do we know what are the ways we can think about answering these issues? The answer is yes. So there, some of them work. This tends to be sensor specific. Again, I'm going to talk about a couple of examples along that line. But great questions. Yes, please.
So I have two questions. One is from YouTube. So somebody asked that in analog circuits, how do you handle the weight change as it happens in the conventional neural networks?
So in this case, our weights are defined as stored in SRAMs. So it is almost just like updating the SRAM. That's a big difference of, instead of, if you use an RRAM or FFET, any of the analog memories, NVMs, it takes a lot more effort to change the weights. But here, this is basically SRAM. So it's as simple or as complex as changing any digital value in any digital system.
Okay, thank you. And another question I want to ask is, I have a more general question. Like, for example, we look at one of the applications, for example, DNN and in images. So our current, the ADCs or DAC that we have are capable so that they can cope up with the real-time image generation or data generation. For example, maybe they are capable for DNN, but they are capable for all set of like databases or some other applications, for example, bioinformatics. So can they handle that, or do we need to look at those part also, so to upgrade those things also?
Absolutely. I think it is basically what you're asking is that, do I need to think about a specialization on the DAC and the ADCs? The answer is absolutely yes. We already do that. That the ADC that you use for sampling a biosignal, which is with a 1 kilohertz bandwidth, is very different than the ADC that I will use to sample radar at 100 megahertz bandwidth, right? So this is already very different. Now the question is that, should we use those ADCs and the DACs directly if I'm talking about within the computing in memory? The answer is no. Because when you start putting this within the computing in memory structure, you have additional constraints, right? You have, as one of the things that I was talking about is the area. You have the constraint that there's a lot more of them working in parallel. So normally the structures that we need to use will be different. And this was a great example, because if you look into current mode ADC, in the normal signal processing, we do not use this, because what we prefer is we take the digital, let's think about an image, right? We have a photodiode, that's your physical signal. We prefer to convert it to voltage directly, and then operate in the voltage domain and using voltage mode ADCs. That is the traditional pipeline for signal processing, right? The reason is that most of our transducer, the way we think, we like to convert things to voltage. But here, and that's the same thought process we applied so far in the computing in memory world also, that you have a current, convert it to a voltage on the bit line and sense it. It turns out that's not necessarily the best way, because the way the signal is generated here is also in my control. So that's the big difference. In the traditional ADC DAC world, I don't control the signal, analog signal. That comes from the external world. So I need to make the ADC or particularly the ADC designed in a way it can control, it has a high SNR, it can support a large dynamic range, so on and so forth, because I do not know how I'm going to use it. But here, I am designing the analog circuits as generating the signal as well, which is the memory in this case, right? So I have a lot more controllability. So instead of thinking of this ADC and the computing in memory and the DAC as independent solution, when you start thinking of this as one big analog circuits, there's a lot more optimization you can do. So a short answer to your question is yes, we have to specialize them. That's basically is what my students taught me. That the more I start fine tuning this, I get a much better performance. So I mentioned this is the first gen. There's a second gen which is currently out there. There's a third gen which got stepped out. All of the changes in this generation are basically tuning the circuit knobs to make it more compute in memory specific and steer away further and further from a traditional ADCs. Any other questions? Okay. So I talked about that. We are going to come back to this figure, because what this figure tells me is the questions that all of you are asking. I think one of you are asking: variations, noise. If we have an analog circuits, and particularly if I'm trying to run at close to a gigahertz level, it's not only variation. We have two sources of error. One is the variation, one is noise, and most importantly is the non-linearity. Because none of the circuits that we talked about are linear in nature. So that brings us to this interesting question that as an analog designer, if you ask me to design an ADC, I will always go for the linear most ADC that I can. And how do you get linearity? The same way, how do you get frequency? You spend more power. So how do you get more linearity? You spend more power. So we ended up over designing. We need that as a separate ADC, but the question that we wanted to ask, do I need that if I'm designing the system as a part of CIM, or is it possible for us to tolerate certain amount of error with some additional means? To understand that question, let's take a system view. Let's think about that I'm trying to use this concept for an image sensor, right? So what you have here is your very basic system, which takes an analog image, convert it to an ADC and send it out. And then you have some sort of a processing node, which is a separate chip. And what this does is that it uses an ML model to operate on the data. Here, if we want to use whatever we are talking about, what we are essentially saying is that instead of this analog input, pass it through this analog computing in memory, which digitizes and generates a set of features, and send these features to the end task. But the part that we have to remember is that the features that I'm generating are going to be erroneous to some extent, because this figure tells me the test chip that we have, if you do an actual dot product math and the result is on the x-axis, y-axis tells you what is the generated dot product math out of your ADC. Ideally, we should have a red line, perfectly linear. I mean, more precisely, this should go from 0 to linear, right? But here we see two problems. We see an offset, which is relatively easy to correct. But more importantly, we see a variance that depending on as you measure it, when you measure it, because realize it's a different combination of the input and the weight can give you the same dot product. But the different combination of the input and the weight is not going to give you the same amount of current, because this is not a linear system. So the problem is, as soon as you do that, it will distort the image or distort the feature, and it will distort your result. So let's look into two parts, that why should I do it and what's the challenge of it, right? So what we were looking at here is that let's think about that this is my input image. Let's think about this is a CIFAR 10 image for the time being. Now I am going to doing all of this the dimension reduction to reduce the dimension of the image by this, by reducing from input size of W to H to W out to WH out, right? So I'm reducing the dimension. So the larger this ratio means less amount of data I'm transmitting, less amount of digitization I'm doing, right? So naturally, as you increase as you increase this compression ratio, which goes from, as I go here, the compression ratio is increasing, I will have less amount of power dissipation, right? Because I am reducing the amount of ADC power, which is getting shadowed down here, and I am reducing the amount of link power, which is the data transfer from the sensor to the processor. But, I am also reducing the VMM power because there is a less amount of ADC within the VMM. But the challenge is, again, as you go in this direction, two things happens. As since you are compressing more, you get more error, so your accuracy drops. But on top of that, as you start considering the linearity of the challenges on the ADC, that adds additional error. So what we wanted to do is to at least to think about how to solve this problem. We were started thinking of, what? Great, so I have generated some sort of an erroneous features. Can I try to restore those features back to as close to the original as possible? So essentially, after you digitize and you generate the features, can I add another simple linear layer now operating in the digital domain and train it to be able to somewhat correct for the noisy losses? You can retrain the entire network, too much overhead. But if you just think about retraining only these little feature restoration engines, it is significantly less retraining overhead. Now, again, if you do all of that, at the end of the day, what we start seeing is that, yes, if you add this feature restoration, it's going to add more energy, but potentially you can still get to a point where if you compare between these two, right, it is less, maybe around 4 or 5% drop in the accuracy, but close to 3-4x change in the energy dissipation. Is it acceptable? Depends a lot on the application. I think this is really where the question of what is acceptable becomes a function of what the application is. If you are using it for a drone to navigate, you're probably in a reasonably free space, it's okay. Can you do that when the drone is trying to land at a specific location and you need much higher accuracy? The answer is no. So you can make it adaptive to be able to deal with how much accuracy changes that you want. Now I'm going to go and talk to about, so imaging is fine, but the power of this kind of techniques becomes a lot more prevalent as you go to the applications where you need a lot higher dimension. For example, radar. If you are not from the radar world, there's an application that almost everyone in the radar and the comm does called beamforming. What is beamforming? It's essentially, let's say you are getting signals. You have a wireless receiving antenna, which is getting signals from everywhere. Some of the signals are carrying information for you. Some of them are either noise or does not contain the information that you are interested in, right? So what do? We essentially almost electronically steer the receiving antenna, not the mechanical part of the antenna, but the electronic reception towards the direction in which I want a higher quality of the signal. So I can try to improve my directional sensitivity. And how do you do that? Let's say you have an antenna that's all receiving signal. You take each of them, and depending on which direction you want to focus on, you delay them differently, and you multiply or amplify them differently. This is called beamforming process. Essentially, you're adjusting the phase shift and the amplitude of all the receiving signal array to improve sensitivity towards certain direction, right? This is a very common thing. It almost exists. Every cell phone that you have, every radar that you can get, everyone does this beamforming, both in the comm world as well as in the radar world. So earlier, we used to do what we call analog beamforming. If I have only a 4 antenna, I can bring these 4 analog signal links. I can design analog shifter, analog amplifiers to do that. As the number of antennas starts scaling up, right? If you look at a TI automotive radar today, it has 4x4 creating 16 different channels. The more newer generation create almost 144 different virtual channels. It's become impossible for us to do it in the analog domain. So we move to a point that what we call digital beamforming. What does it really mean? Is that you take the analog RF antennas, RF input, you go through the standard RF processing pipeline, you come back to the baseband, and then you digitize. And after digitizing, you do a digital phase shifting, which is basically just digital delay, that is at flip-flops, right? You shift the phase in the digital world, and then you do digital multiplication. So this engine is a large multiply and accumulate engine, right? But the challenge is this is operating at very high rate. Some of the wideband radars, we want to get close to a gigahertz bandwidth. So essentially you are thinking of this entire ADC, the phase shifting and the way this is all operating at a 1 gigahertz or higher data rate. Now, if you take everything that we have talked about so far, I can very easily transform this design to something much simpler. What we do is that we bring in all the signals, but instead of digitizing, we pass it through this feature extractor, which reduces the number of dimension. And then we do all of our digital computation on this reduced dimension, right? Can I use exactly the same delay and the weight? The answer is no. I have to retune all of the filters. But the point is, you can see two things that's happening here directly. I reduce the number of ADC, but also I reduce the amount of digital computation. This concept exactly going to scale if your backend is not a FIR filter, if your backend is ML model. Because we are reducing, by doing the dimension reduction, you reduce the analog compute part or analog part of the ADC, as well as you reduce the digital baseband processing. And the implication is, okay. Now, after you do that, there's few more algorithmic concepts that we need to think about it, because, ideally we would want full analog precision, but maybe your memory is only giving you 4-bit precision. So what do we do? So there are compensation techniques that you can develop, which is essentially working at a much slower speed, right? Digital techniques that allow you to essentially design these weights in a way that they can operate with a lower precision and still give you the same accuracy. So normally, if you look into an RF beamformer, we look into this specific plot. What this plot tells us is that what is the SNR in the signal to noise ratio of the original signal in your target direction, and this is what is the SNR of the signal on the target direction after beamforming. So unless this one is significantly higher than this one, it doesn't make any sense, right? I mean, why would you do all of this computation and then your SNR on the original signal and the beamform signal remains the same? It doesn't make any sense, right? So we always try to get an SNR gain. 30 to 40 dB SNR gain is considered to be almost like what you want to achieve. So what this figure is telling us is that with quantization and more importantly this quantization compensation, it is possible for us to maintain that SNR gain. So long story short, I can maintain my accuracy. How do I do that? Is by co-designing or co-optimizing the filters that are processing it and this SIM that is sampling it. If you transform into the ML world, what does it mean? This becomes your weight of the neural network. So then you co-tune the weights of the neural network and the front end together, you can achieve the similar objective. But why do we care? So this is estimated power for an antenna, where let's say you have an you have 256 input channels, and you are trying to generate 1 output beam or 16 output beam out of it. The blue ones tells you is your RF power. We, at least my group, we cannot do anything about it, right? So I'm not an RF designer. Talk to folks like Professor Hua Wang here. There are folks all over the world who are spending a lot of effort in reducing that number. So 100 milliwatt per channel is considered to be, a really good number that people are thinking of. If you look at an TI radar today, that number is around 300 milliwatt. There are academic work which tries to push it down to 80 to 60 milliwatt, right? So think about it. If you are an antenna designer, you would want your RF front-end power, as you scale it down, you would want your system power to scale down proportionately, right? Now, let's look into this bar. This one is telling us a very interesting story. This tells us is that this power dissipation associated with computing this digital FIR filters, that is this ones, which is essentially multiplying, shifting with the shift registers and multiplying. A very simple logic, but a lot of it, and running at a gigahertz speed. You start getting to the point where this might start dominating your system power dissipation. So to answer your question, does the sensor power always dominate? The answer is it depends. So if I look into this example where I'm generating one output beam, the blue and the green dominates, the compute is very less. But here, when I'm trying to generate 16 beam out of the same information, it's almost like if you are trying to detect 1 million objects in your imager versus 2 objects out of your imager, that changes your back-end computation pipeline, right? And you can get to a point where this might start to dominate. So now when you are thinking of in-sensor computing, this is not only about reducing this green one, which is the ADC energy, the way we started off. And that is the primary factor if you look into this example. But as we go from here to here, you can see the main benefit of dimension reduction comes from not the ADC power reduction, but the reduction in the background power. So being able to extract features at the sensor, reduce the dimension, helps you to reduce your digital computation power that's on the back end. So you get both types, both the benefits simultaneously. So hopefully that answers the questions that you had in the beginning. So that's the reason we need to start thinking about how much computation I can do inside the sensor to reduce the amount of data that's coming out. Okay. I think I'm going to skip this because the next one is basically telling us, it's a bit more detail on the radar side. It basically tells, I think, the question that was on the YouTube, that do I have to write this weight? The answer is yes. You cannot, it is not like a neural network inference where you can have a network weight and leave it there. You cannot do that because as the drone is navigating, the direction that you want to focus on might changes, right? If you figure out I'm trying to follow an object and the object is moving, my directional sensitivity has to move as well. And to do that, I have to continuously update that metrics that I'm using to extract features. Don't worry about what the subspace error means, but think about you want the y-axis to be as small as possible. If you do not adapt this metrics that we're using to change, you get to somewhat like the green curve, which is not desirable at all. If you can adapt it properly, then you can get to something like this one, which is much better, close enough to the baseline system. So the point is, once you bring in the SIM, we have to also keep in mind is that feature extractor must be adaptive. If not, that's a problem. So what that means is that the traditional metrics of reading and the writing from the memory cannot be ignored. You still have to be able to write to that memory faster. I'm going to skip that. The last part, maybe 1 minute I'll talk about this, is that now when you... Oh, yeah. No. I think I spent a minute on this. I want to a little bit talk about the optimization problem because I think some of you might be interested and you might be interested because we should talk about that later. Another factor that's interesting for us to remember is that when you think about analog computing in memory, right? If you think about a digital computation, what's the first thing that, no, I shouldn't say the first, or what are the things that we think about reducing power in a digital computer? What are the ways? If you take a VLSI, 100, I don't know what is the lowest level marking here, we call it 100. What are the things that we do to reduce power dissipation in digital circuits, right? Scale your voltage, that helps. What else? Any ideas? Scale frequency, what else? Anyone remember the formula that tells energy is equal to C VDD square plus power plus this? There's one more thing on that term, the term called alpha. That's the activity, right? So activity is one of the designer's best friend to be able to reduce power, because if I can reduce activity, I don't have to deal with voltage scaling, don't have to deal with frequency scaling. I can get a linear benefits in power. How do we realize that in this analog computing world? Let me take a step back and go back to this figure. If you look into this figure, where are we dissipating power in this analog compute? Just think about it. This SRAM cell doesn't do anything. I mean, it's forget about the leakage power for the time being. The SRAM cells don't dissipate any power, right? Take the leakage out of the picture. We don't have any switching at all. So there's no switching power. But whenever this cell is on, what happens? Depending on the input voltage, I draw current from this line, right? So now if you look into a column, more and more cells in the column, which is storing 1 here, means I will have current, more and more current drawn. So now if you think about a weight vector, for the time being, assume a single bit vector. If you think of a matrix where every weight is a single bit weight, if the weights are 1, I'm going to draw current. If the weights are 0, I will not draw any current. Now, think about, so what can we use to measure how many ones and how many zeros that we have in a word, or for that matter, any digital file? We call it Hamming weight, right? So Hamming weight of a word tells me how many ones I have on the bit vector. Hamming weight of an entire matrix will tell me how many ones do I have. So your power dissipation is going to be directly proportional to number of cells storing 1. It's also going to depend on your input. We cannot control that, but we can definitely control the metrics. So if I can start rethinking this whole notion of quantization, pruning, and everything that we know in the standard DNN world, if you start rethinking of them in the analog compute world, we can start using this whole notion that, what is the weight, what is the Hamming weight of the column that I'm storing? And I minimize the number of ones, not the weights, number of bits that we have. So for example, if you have a bit which is 0, 1, 1, 1, instead of that, if you make it a 1, 0, 0, 0, you're going to reduce power, because instead of 3 ones, now we have a 1, 1, right? So you can think of it as a quantization, but more importantly, you can more directly start thinking of it as an Hamming weight. So generate weight matrices such that the Hamming weight is lower. So we started, we thought about this concept, we had a couple, and you can do that. You basically bring it in as a part of your loss function, so that, you promote neural network, and in this case, that promotes the AFE matrices, which settles with a lower Hamming weight. And once you do that, you start saving potentially even more energy dissipation by reducing the number of Hamming weights or number of ones that you have. Yes, you have to keep in mind is that, you don't want to make it all zeros, because then your accuracy will fall apart. So you have to put a loss constraint with an accuracy constraint. But this is an example where a very well-known technique in the digital world, which is activity, you can transform it in this analog computing world through a little different metric, but you can incorporate that same concept of reducing or changing the bits themselves to be able to reduce power. Okay, I'm going to stop here for a couple of minutes before I switch and very quickly go through this optimization part. Any question here? Yes, please.
So there is a question on YouTube again. Somebody asked that as shown in measurement result slide, the mean error is around 6%, which would correspond to an effective resolution of around 4-bit, whereas we expect 12-bit for multiplications. So now, is this a limitation from the ADC itself? For example, the current presented is precise, but the conversion is not good. Or whereas it's the same architecture that ADC is good, but the sum or multiplication is not good.
So it's probably not obvious from the data, but on a most post-processing, it's a combination of the two. So there is the newer versions are giving us much better results, and one of the reasons is that part of it is the ADC, because the way this specific ADC was designed, it has whenever there is a step jump, the errors were a lot more. So that's one. But part of it is the CIM, but most of the error is coming from the ADC in this particular example. And DAC also. Yes, please.
So since we are talking about the Hamming weights based quantization, right? So do we encode the weights in a different manner than, let's say, the binary encoding? Because binary encoding keeps switching bits quite a lot, right? So let's say, for example, if you go from 3 to 4, like all 4 of bits would be changed, right? But if we go for a different encoding, like if we just simply reduce the Hamming distance from one to the other, does that affect also power in this case?
It's a great question. I think in the analog case, since once your weights are, unless you are changing the weights, right? Let's think about the scenario. I have a weight stationary part, right? The weights are stable. In this case, the Hamming distance matter less than the Hamming weight, because if you have a 1, you're going to consume power. If you have a 0, you will not, right? Now, if you think of in the analog case, when you will get the Hamming distance change is that when you're rewriting the weights. In this case, the more the Hamming distance, the more will be the write power. It's a little different in the digital world, because digital world, if I'm having particularly if I have a multiplier that is multiplying between different weights and different inputs, the same multiplier, that's sort of having the input state, I mean, particularly if I have an input stationary model where input is constant and the weights are streaming in. In this case, the Hamming distance matters a lot more, because same input now, if the 2 consecutive weights changes, you have a more switching on the bit. So in the analog case, the Hamming weight is more critical in terms of the inference engine than the Hamming distance. Now, I think in the digital world, particularly if you have an input stationary weight flow model, your Hamming distance might become. Now, you actually have asked a more profound question, that the encoding. There might be better ways to encode. So currently, it's not the encoding of the a specific weight value to the bit precision, but how do you generate the weights? Are there better ways? Can the entire neural network be thought of operating on a different transform domain itself? So there are very interesting, again, we haven't done it. I know some of my collaborators in our center, again, you can read up the papers from University of Michigan. There's a group from called Professor Hans-Georg Kim and David Blau. They have done some very interesting work where they have shown that if you do an Hadamard transform on the weights, before you even write, you can actually reduce power dissipation. So there is the question of do we encode it differently it has a lot more profound implication than Hamming weight and Hamming distance. So the large case, your answer is yes. We should think about what's the right way to transform the weights to be able to reduce power. Any other question? Okay. So I'm going to go very quickly on the second part because I don't definitely want to go beyond 12:30. So on the edge, we often do another problem, right? This is what we talked about here is perception. We also need to do decision making. right? And one of the part of decision making is often solving optimization problem. There are classes of the optimization problem which are known as hard optimization problem, which are either NP complete or NP hard. One example is SAT. And most of you are CS students, so SAT is something that you probably already know. It's basically, if you have n variables and if you have m number of clauses, can I find out assignment of the variables that makes all the clauses true, right? Now, it's a very well-known NP-complete problem. It's used in many, many, many different places. Tons of work has been done algorithmically to be able to make this thing faster. So in general, as you increase the number of variables, the time it takes to solve this problem increases exponentially because it is an NP problem. So one of the area of research in this SAT solver has been, are there ways for us to more efficiently solve the SAT problem? Now, taking a step back, if you look into the CS world, when we say that solving a SAT problem, it means there are two classes of problem that we do. One class of the problem is that I give you a clause. I mean, I give you a set of clauses, and I ask you, is this set solvable? Give me a yes/no answer. I don't want to know what variable set solves it. Is it solvable? This is a very classic problem. It has a lot of theoretical interest. There's a second part of the problem where we say, I give you a SAT problem that have a number of clauses. Give me the assignment of the variable that actually solves it. Why do I need that? Maybe I'm trying to optimize, right? I'm trying to find out the best path to go from point A to point B. Maybe I'm trying to find out the most optimal routing on a chip. Many of these cases, I want to find that assignment. If you are trying to find that assignment and if you can get to the optimal, great. But by definition, you cannot find an optimal solution unless you are spending infinitely long amount of time, right? Because it's an NP-complete problem. So you can only verify whether a solution works or not. Then the problem essentially translates to how quickly I can search the entire potential assignment space. If I can search it quickly and I can get to a near optimal solution very quickly, what it really means is that I can make a decision that what path I should take to go from point A to point B. It may not be the most optimal path, but it is potentially within 1-2% of the optimal path, but I can make that decision 100x faster than what it will take me to get that last 1%. It may make a huge difference in certain application. It may not be acceptable depending on what's the cost of that 1%. So if it is acceptable for you to get to a near optimal solution, but you want to get there very quickly, this whole domain of SAT solving in hardware starts becoming important. So essentially, the way we think about this problem, we mean in the community, is that you have a vector. You can think of it is a random vector. And I look into many different random values of this vector. For each of them, I find out how many clauses I am solving. If I have a pure random solution, it's going to go wherever, right? I mean, there is no guarantee of convergence. So if there are ways that you can make it converge, and converge faster, there's a lot of interest in that space. So one of the ways that we have started looking into this problem, and again, this was, I will refer you to this ISS and the JSS paper for more details, but the whole point is, instead of making these random searches completely independent of each other, if you can start bring in a little bit of Markovian into the process so that your behavior of the solution on the guess one somewhat dictate what are you guessing in the second one, it helps in navigating the problem space faster and approaching the optimal solution faster. You can do that by creating this notion of an recurrent network, which essentially emulates a Markovian process, that what says that your current state and some weights will tell you what should be your next state. So essentially, you bring in this recurrence into the system. It is not a perfect, not a normal recurrent network, because if you just make the first decision and then make every other decision deterministic, that doesn't work. So you need to have what we call a stochastic recurrent network, where every time you generate a stochastic set of neurons, you use that state to determine what is the next potential state, but then you add some stochasticity on top of that. So you can navigate this search space. Otherwise, what will happen is that you will get stuck over here, right? To go from here to here, if you just using a gradient approach, is not going to let you go there, right? So you need some sort of a randomness that allow you to go over that. And you can realize this. I'm not going to go through the circuits anymore. Enough of circuits. You can realize it using these analog SIMs. You can have one analog SIM that acts as a recurrent network. You can have another one which basically tests whether the solution that you generate, what's the cost of it, and then based on that cost, you can start to decide, am I going in the right direction or not, and accordingly you change the probabilities. The reason the analog SIMs becomes very interesting here is that all the problem that we talked about earlier, that I have variation, more than variation, I have noise, there's a non-determinism. That's not that big of a problem in these domains, because by definition, my neurons are stochastic, right? So a normal noise is not a problem. Variations are a problem because you don't want to bias the search, but the randomness in the process, which is often the reason for the spread, just the natural randomness, is not necessarily a big issue. And we did a test chip on this. What's interesting is, do I have the result? Yeah. So normally when we look into the SAT problems, the way we define how difficult this problem is by this term called CVR, that is clause to variable ratio. That if you divide the number of clauses with number of variables, the larger this number is, the harder it is for you to find the solution. So normally 4.3 or 4.2 is considered to be what we define as a hard problem. Why 4.2? Why not 4.3, 4.1? That's not the discussion that I want to get into. That's beyond the work that we do. But statistically speaking, if you talk to the computer scientists, they tend to come up with this some number, 4.2 something, as a boundary of a hard problem. So what we wanted to understand is that what happens if I do this analog computing based circuits, and the results are very interesting actually. I would say this is even more interesting than using these things for a DNN acceleration, is that if you start looking into how quickly I can get to a good enough or very good solution, dramatically increases by using these classes of computing in memory approach. And you get to, the for an 4.2, 4.3 CVR, you can get to almost 60% solvability even for 40, 50 variables problem, which is very hard to do using traditional techniques. More importantly, if you look, for example, that I want to solve a 60 variable problem, hard problem with a 4.2, and I want to get to 99% satisfiability. As long as 99% of my clauses are satisfied, I am happy. If you run this on a CPU, it takes hundreds of seconds, because the way the CPU would work is that it's trying to really find that best possible answer, right? That gives, and then it will compute what is the satisfiability score. Compared to that, when we start getting into this search-based methods using the stochastic search, it can get you there with almost 1000x faster, 100x to 1000x faster at a small problem level. This is really interesting and very encouraging results that we are seeing. And I'm not even going to talk about the power advantage of it, because that's kind of obvious, right? It's an ASIC versus CPU. But the speed advantage are really interesting. And there are techniques that we are looking at. And again, to think about how do you go from a 60 variable problem to 60,000 variable problem, how do you distribute it? There's an entire new field now opens up that how do you take this kind of an stochastic recurrent network-based coarse solvers and design large-scale solvers. This is some of the ideas. Getting within the DRAM makes a lot of sense because you have to have these variables, update them quickly, not a small scale, but a large scale scenarios, and you doesn't have to do it in the analog way. Because basically this is the algorithm. You can have this SNN CIMs and the RNN CIMs designed using digital logic, still much more efficient than doing it with an CPU and the GPU. But the point is, this is now we can start thinking of CIM being applied to an entirely new dimension of problems, which is solving hard optimization. SAT is one example. Another really well-known example here in this domain is least square problem, particularly an integer. Again, I'm not going to go through all of the details here. Integer constraint least square. If you have a cell phone today, it is doing it. Because one of the very important problem that we want to do in any kind of an RF domain is that we basically are trying to do this mapping of the symbols that I'm getting to the original symbols they should be. And this is often becomes a least square problem because you get a noisy set of signals. From the noisy set of signals, you are trying to estimate what was the original signal that was sent through this wireless channel. It's a very classic integer constant least square problem. Time consuming, expensive, and depending on whether it's a COM versus, if it's a voice COM versus image COM, depending on that, you have a different level of tolerance. There's a very classic work from Hofeld back in 1986, where he had shown, and he and his students have shown that I can solve these classes of problem by mapping them into a resistive crossbar. But we couldn't do much with it because we didn't know. We still don't know how to create resistances with very high precision. But if you look at the analog computing in memory world, we are creating those resistances with decently high precision, not by making them resistor, but making them digital word and dealing with all the challenges that we talked about earlier. You can start implementing them again using these analog compute memory solutions, but you build this compute arrays and let this dynamical system work so it settles down to your optimal solution. I'm going to skip it. The main advantage, again, this was a 65 nanometer test chip. The main advantage that we start seeing is down here. If you are, let's say, trying to solve and 64 variable least square problem, I'm going to skip some of this. I'm going to come to there. Using these classes of in-memory compute, you can start getting almost 1000x to some cases 10,000x speed up of solving it in this chip versus trying to solve them in a software environment, which is not surprising because software to hardware, but the fact that now you can, when you are designing these macros or these concepts, we see another domain of applications where the impacts are very significant. It's almost think about you're trying to transmit and if you can make these things accurate, which you can as you get to more digital version of some of these computing in memory approaches. But point is, once you get there, you start seeing this least square problem, that is how quickly your cell phone can recover the original symbols. If I can do that 1000x faster and with a 1000x lower energy, that dramatically drops the overall energy dissipation of a communication front end, particularly of our communication systems. So again, I'm skipping some of these details. The slides I already gave it to Anuj. So if you're interested, we're more than happy to talk. But what I want to end it with saying that, yes, computing in memory has emerged as an important topic. And if you look into the literature, there are a lot of literature telling us how to do it, what are the different ways of doing it, looking into DNN or the AI as a target application. What I tried to do today was to sort of give you an exposure that if we are developing this technology, it is just not for AI. there is a many different applications domain where the computing in memory classes of technologies can give you tremendous benefit. There are two examples that I went to. The first one I went to a little bit more detail, which is using it for a feature extractor at the sensor front end. There are more interesting ways of using this as a feature extractor, and we can talk offline about it. But the whole idea of using it to directly operate on the analog signals to reduce the dimension is very attractive, gives you, orders of magnitude benefit compared to what you can do today, even with all digital custom design, right? Compared to that, you get tremendous advantage, and it's very clear why do you get it. The second, what I was trying to talk about is you have these very hard optimization problems, and they now find an interesting way of solving them that gets you to a good enough answer very, very quickly. So I hope that there will be more effort which is trying to go beyond DNN acceleration and start thinking of computing in memory, analog, digital, in DRAM, in NVM, in SRAM, to problem domains outside of DNN. With that, I'll stop and we'll be happy to answer any more questions that if any of you have. Okay.
Any other questions?
I know I'm standing between you and lunch, so
Yeah.
that's never a good place to be.
Yeah, you must be hungry also, but
I'm just waking up from the
okay, that's true. Yeah,
time, so it's okay.
That's true. It's the waking up time in the US, in the East Coast at least. No questions? Maybe I'll ask a question.
Sure.
Actually, maybe two questions. I think this is very, very interesting and it's exciting. I really enjoyed it. I have a question on like applicability in general to data set sizes. This is SRAM, which is very interesting. No question about that. You can do more modification in SRAM, which is a lot harder to do in DRAM. But how large data set sizes can you handle in SRAM in realistic situations? Versus when do you need to go to DRAM? And how much of the data movement is a bottleneck right now because you cannot fit it in the memory?
Yeah, I mean, I completely agree with you. So my answer, basically, that is essentially the question that you're asking is that I potentially, if I'm trying to accelerate a DNN, it's very unlikely I can feed the DNN in, right? So I basically going to get a compute engine out of this. And then I have to go through the same data flow, data movement. Absolutely true. That's basically the reason I'm saying let's look beyond DNN. These particular applications, you are not really looking at a data sets anymore, right? And the part that you are trying to solve is not necessarily the data movement, but data digitization of the data. That's one, right? So in these cases, the memory that I'm using is actually very small. So even for this 1024 radar example, the size of the memory that I have is 1024 rows and maybe 1024 columns. Very small array. But the potential advantage is tremendous. The reason is we are using it to remove a different bottleneck, yes, not the data movement.
Sensor side, essentially.
Sensor side, right? Now, you are absolutely correct. If I am really using at a DNN accelerators, we have to keep that in mind. If the models become larger, it does not help. And the second part, it doesn't help. Now, let me talk a lot about the problem I have with computing in memory. It helps if your weights are stationary. So if you look into, let's say, an LLM, a transformer, for computing attention, I don't want to use this. I mean, I have seen work that do that, but I have both inputs and the weights are varying at the same time. That means I keep on rewriting. Even if I'm not forgetting about the data transfer, I'm just rewriting this all the time, right? Because I have to, when I do the attention computation. So how do we do it? We do all this KV caching, bring these things in. But at the end of the day, am I going to get a lot of advantage? It's not clear. Yeah. So we get a very high tops per watt and the tops per millimeter square with these models. So you have to think about what the right way to use them.
Yeah, makes sense, I think. One question I have is like in SAT solvers, for example, if you want to scale to much larger.
Yeah, so that's actually an interesting point. So what we have seen, you can actually scale it. I mean, again, I didn't talk about that, but we have a realization we can scale it up to 60, 70,000 variables. It's pretty large scale because, if you look at, again, the memory requirement here is not that much, right? Because your neural network is essentially n cross n. It's so that recurrent network that we had, right? So this is if we look into one of this block, where is this thing? This guy, right? It has a dimension of n cross n. So if you think about, if I want to make a 60,000 variable SAT solver directly with this, it's not going to work. Not because of the size of the array, that's not too much, right? It's a 60,000 by 60,000 is still within megabytes, right? Hundreds of megabytes. But the problem really is that that's going to be a very, very slow memory. So now the real challenge of scaling it up here is more of a distribution algorithm. So you will have to have small cores, and then you will have to distribute the weight matrices, or not the weight, rather the variables properly, so that the communication between these blocks becomes smaller. So it's more of an distributed computing, distributed optimization problem rather than, and as a part of that, there is a data movement problem that exists, but it's not necessarily the capacity problem. I completely agree with the capacity problem when it comes to neural network acceleration, that I can only do very small network before I have to bring things from DRAM anyway. So then maybe the question is, again, I'm not sure whether you are aware of, that there are papers that talks about doing this analog computing with DRAM. Maybe they become more attractive, but it's much harder than doing it in the SRAM systems because
the operations you can do is much lower at this point, but
so
there could be other approaches.
It's a very valid question. I would be very interested in seeing a good study that talks about model size versus efficiency, considering the DRAM data movement, and when this computing in memory does not make any more sense.
I think it makes a lot of sense, but we can take it offline. One other question I have is, okay, this is a tough question always memory designers ask. I think you have a great mindset, like maximize the memory area. But if you keep adding these for different applications, you're still back to kind of square one, right? Memory designers still needs to add a lot of logic, and memory designers don't want to add anything in general to their memories.
Absolutely. So the first absolutely true. There are things that we didn't talk about. I mean, I can talk about a lot of this because I used to be a SRAM designer in my IBM days. So I know the pain points. So the first thing that whenever we are talking about the SRAM, right, we are modifying the cell. As soon as you modify the cell, it essentially becomes a logic DRC, because no memory foundry will let you use their memory DRC rules, right, as a designer. So right there, you lose density by a factor of 2. So that's one of
I was going to ask that actually. Is that density loss included in your measurements?
Nope.
Okay, so there's additional density loss because you go to 80 and this type
no,
of
so
circuit.
your 80 is included, but what is not included is the fact that because there is no way you can include it, is if you actually get and compile the SRAM that is based on the foundry design memory, you cannot do that just because the SRAMs breaks all sorts of rules, right? And you are not allowed to break that if you are designing yourself. So there is a density loss right there that is not captured in any of the computing in memory work that you would normally see. And that's really where the digital computing in memory mix, if it is supported by the foundry, will always give you more density. Not because it has less energy, just because they're allowed to break the rules and they can break it in a way that they know it's not going to maintain the yield. The second factor that is, even in this case, that makes important is that once you bring in this logic, right, you break the regularity. And as soon as we break the regularity of the memory, the yield goes down. So how does that layout, the density variation plays a role. It's very hard for us to evaluate even because we are not using the right DRC rules at all. TSMC can do that potentially, or any foundry can do that. I'm sure that they may do it. Not sure whether it's available publicly, but that's another density faction that is important. So important problems.
So, yeah, I'm just delaying it again. So when you're talking about, let's say, 60K, 70K variable solving, right? And then you said that we cannot afford to have it in a one blob of memory and then just map it there. So we need to have distributed blobs of memory. So when we orchestrate the communication between these distributed blobs, right? So do we again switch back to something like a gated, like a synchronized fashion? Like, does that require thinking in the digital realm, or?
Absolutely, it requires a lot of thinking in the digital realm. We have a solution. Hopefully, when the paper is published and everything, I'll be more than happy to send it to Onur to take a, and he can send it to you. But not necessarily that's the best way, right? So we have one way, but you are absolutely correct. It requires thinking in the digital realm because it requires again. I mean, if you take a step back, this problem of solving large-scale SAT using smaller cores is there. It's always been there. It's a distributed optimization problem, right? There are many different methods that people use for distributed optimization. What I would say is that what we found is that some of them are more amenable to these classes of core. Some of them are more amenable to if your cores are doing the standard CPU-based computation. But your answer is absolutely true. We need to think about the communication. It is a digital problem I mean, first of all, it's a mathematical problem, but the right way to, you can heuristically, you can guess, right? I mean, what you want is that not all of your clauses have all variables. If all of your clauses had all variables, then you need the full 60,000 by 60,000 metrics. There's no other way you can get out of that, right? So what it becomes is that when you are mapping this, you try to find out the clauses which does not share variables. They can go independent, right? When the clauses share variables, they need to talk. So if you can map it in a way that the number of minimize this and put them closer, physical layout, those are the things that will help you. But fundamentally, that's the thing. If they share, they have to talk. There's nothing you can do, nothing anyone can do about it. So that's hopefully that gives you the intuition. Thank you. Very engaging discussions.